part 2, we're talking about the strong nuclear force, and the strong nuclear force is what holds the neutrons and the protons together in the nucleus. And that brings us to the concept of binding energy. So the question is, and it says, as long as the nucleus is stable, energy must be added to separate the nucleons from each other and move them far enough apart that the strong nuclear force can't hold them together. This is called binding energy. Now, binding energy is sort of one of those kind of backwards concepts because of this right here. Since energy must be added to move the nucleons apart, separate nucleons must have more energy. When nucleons are bound in the nucleus, they have not had energy added yet, so they have less energy. And if something has less energy, according to Mr. Einstein, then it must have less, there it is, it must have less mass. And here's our probably most famous physics formula, E equals mc squared. And as you can see in this formula, Mr. Einstein says there is a direct relationship between energy and mass. So something with more mass has more energy, less mass, less energy. Now, what this means is that if you have a whole bunch of nucleons just separate, so you got a couple of neutrons there and a couple of protons there, and you want to combine those to make, in this case, a helium nucleus, 2 protons, 2 neutrons, or an alpha particle. If you want to combine those, you must take some of their mass and convert it into energy so that they can form a nucleus. Therefore, the mass of this is slightly less than the mass of these 4 things when they're combined or separately. So when they're separate, they have a slightly greater mass than when they're combined, which is sort of counterintuitive, but it makes sense. We've got to take some of the energy, some of their mass, convert it to energy to make them into a nucleus. And that's what binding energy is. So it says, so since separate nucleons have more energy, they must have more mass. Nucleons bound in the nucleus have less energy, so they have less mass. And then you get this. If you're not familiar with this terminology, this is sigma. Sigma means the sum of. So this is the sum of the mass of the protons plus the sum of the mass of the neutrons is greater than the mass of the nucleus, which is, we said, there's a good example of why this is sort of counterintuitive. It would be, in your next page, you said it would be like building something out of Lego pieces, and in the end, it weighs less than what the individual pieces weighed at the start. Well, that is because some of the mass needs to be converted to energy to hold it together with the strong nuclear force, and that's called the binding energy. The difference between the mass of the nucleus and the individual nucleons is called the mass defect. And the mass defect is really what's in the F equals mc squared formula. The mass defect is related directly to the binding energy added to break apart the nucleus according to the formula equals mc squared. Okay, so now the rest of this lesson is just going to be doing example number 3. Example number 3 is one of those questions you'd never see on a diploma, but you might see elements of it on a, oh, what a good pun, elements of it on a diploma or on a unit exam. So we're going to do the whole question. It's a pretty involved, intense question, but it's an important question to teach you about all the concepts of the nucleus, binding energy, mass defect. So the question, the mass of a zirconium-93 atom is 92.90647 atomic mass units. Determine the mass of the nucleus, the mass defect, the binding energy of this isotope of zirconium. Don't worry about significant digits for this question. All right, so the first thing we're going to do is identify zirconium. Zirconium has, well, identify how many protons and how many neutrons there are in a zirconium-93 atom. So in a zirconium-93 atom, there must be 40 protons. And how would you know that? Well, you'd look on your periodic table. Therefore, there are 40 protons, and it's zirconium-93, there must be 53 neutrons. Okay, and since we can assume that it's not, that it has a neutral charge, then there must be 40 electrons. Okay, so now we've got some basics about zirconium-93. Now, the first thing we're going to do is find out what the mass is. Determine the mass of the nucleus. Determine the mass of the nucleus. Mass of nucleus. So this number here represents the mass of the whole thing. So to get the mass of the nucleus, actually it's pretty straightforward in this question. We're just going to take the mass of the atom and subtract the mass of the 40 electrons. That one's not too difficult. The mass of the nucleus is going to equal the mass of the entire atom minus 40 times the mass of an electron. And those numbers are given to you earlier on in this lesson, what the mass of a single electron is. So we're doing everything in atomic mass units here. And that gives us an answer of 92.88 4526 atomic mass units. So that's the mass of the nucleus. It's just the mass of the entire atom minus the 40 electrons. Number 2 asks for the mass defect. So before we do that, we're going to need, to get the mass defect, that's going to be the mass of the nucleus, or it's going to be the mass of the nucleons minus the mass of the nucleus. So the mass defect ran out of room. The mass defect is the mass of the nucleons. In other words, the mass of the protons and the neutrons, if they were all separated from one another, minus the mass of the nucleus. Because the mass of the nucleus is going to be slightly less because we take the mass, we take some of the mass of the nucleons, convert it to energy to keep the nucleus together. So now we have to find out what is the mass of the 40 protons and the 53 neutrons, and then subtract the mass of the nucleus. So that is going to be 40 times the atomic mass of a proton. Let's just write it like this so everyone understands. Plus 53 times the atomic mass of a neutron minus the mass of the nucleus. Okay, so now you've got that. It's relatively straightforward. It just involves a lot of long numbers, and it's a tedious process. So this is going to be 1.00272765 plus 53 times the mass of a neutron, which is 4.9 minus the mass of the nucleus, which we did in the previous question. All right, stick all that into your calculator. and you are going to end up with 0.8657737U atomic mass unit. So remember, that's not in kilograms. And we're going to want the answer in kilograms eventually. So that would be an acceptable answer. But we're going to want it in kilograms eventually because the next question asks for the binding energy. And remember, the binding energy, we have to use the mass defect for the binding energy, and we use it in kilograms because the speed of light is in meters per second. So we're back to using fundamental units. So we're just going to convert that. We're going to convert that to kilograms, and we know that 1 atomic unit equals, what was it, 1.660, I can't remember the number, 660, let's just write this down, 1 atomic mass unit equals 1.660539 times 10 to the negative 27 kilograms. Therefore, this number here, 0.86, blah, 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 equals, it turns out to be 1.4376, 1.43765. Oh, goodness grief, why did I do so many digits? 0.99402 times 10 to the negative 27 kilograms. There's no need for that many digits, but you should keep at least 6, I would say. Anyway, so there's our mass defect. And then for the binding energy, the next part, number 3, the binding energy, it's just going to be E equals mc squared, where this is the mass defect. And obviously, you're going to keep all these numbers in your calculator, so you don't have to be punching in all those numbers together. So take that, multiply it by the speed of light squared, and you are going to get 1.2939 times 10 to the negative 10 joules. Okay, so that's an acceptable answer. Now, just because we like to make things even more complicated, when we're talking about binding energy, we don't like to express the answer in joules. We want something a little more convenient. So we're not just going to change it to electron volts. We're going to change it to something else. So let's first change that to electron volts. So if I change that to electron volts, I get 8.08 times 10 to the 8 electron volts. So you're talking about a pretty decent amount of energy, but physicists are not happy with that answer even. So because these numbers all turn out to be in a similar unit, we actually like to express this in mega electron volts. And the question is 8.08 times 10 to the 8th electron volts is how many mega electron volts? Well, if I move the decimal place 2 over, 1, 2, it would be like changing this from 8 to 6. And we know that 10 to the exponent 6 is mega. Therefore, the answer is 808 mega electron volts. Okay, that is the binding energy of a zirconium-93 atom. One single atom, that's its binding energy. And now you're probably starting to understand why the sun, for example, can give off so much energy over such a long period of time, because that's the binding energy of one single atom, one single nucleus of zirconium-93. Okay, that's the end of this lesson. And we're going to continue with alpha, beta, and gamma decay in the next lesson.